Okay, good afternoon. Welcome to our session. My name is Chih-Tsung Huang, and my co-presenter, Wei-Jen Huang, are part of Cisco's Common Hardware Group. Together, we have many decades of experience in debugging and diagnosing many generations of Cisco products. In this session, we will discuss generative AI applied to diagnostic testing on OCP switch. And specifically, we will share our view on the evolution, limits, and possibilities of generative AI. A very important metric that defines if your company has joined the big leagues is determined by how long it takes you to reach 100 million active users. Let's compare key companies of the past 2 decades, including Instagram, Spotify, Uber, and others. As we witnessed in 2022, ChatGPT achieved this significant milestone in 2 short months. And we will see that is 35 times faster than Uber. ChatGPT made a really big deal out of everything because the thing is everybody actually used it very quickly and really made the progress a lot faster. Now, ChatGPT is based on a large language model, and which is an enabler of the technology. And what is the simplest form of a large language model function? In the most classic form, it is an application that allows users to ask questions from a prompt, and that such a large language model will return the best response based on its knowledge. And this is a very, very simple example. If the prompt of 1 + 1, as we know, based on the knowledge it has, it returns the number 2. Now, large language model, has evolved significantly in the last 3 years. And I will show you that actually how it has evolved really significantly. So I call the first one the classic model. Basic is a simple prompt, question and answer. Then the next thing that evolved is what we call custom. Custom is basically a form of actually better knowledge, and actually one can actually add your own proprietary information to it. Then we actually have enhanced agentic, and eventually multi-agent. So this evolution I want to share is actually thinking about how it's been done, and let's talk about technologies. I think we all know that made this happen. So as we can see, the technology that had made this happen initially was pre-training. So a pre-trained model from Wikipedia and the whole world gave us ChatGPT and the common knowledge. Fine-tuning enabled us to actually do better with proprietary information. Retrieval augmented generation is another technology that is an enabler. And finally, agents and multi-agents. So these are really terms that we have heard about for many times in different articles. So I'd like to elaborate just a little more on each one and really show a pictorial diagram of how this works. So since the 3 years, I think we have seen classic large language model that's evolved rapidly. Let's do a deep dive of how each one works. So pictorially, you can see the first one is with the pre-trained model, as we talked about earlier, is a very classic question and answer. The second one is what we call fine-tuning, where we actually augment our company data, for example, employee database. So that we can actually ask a question, right? It will actually not only use a large language model of ChatGPT and others, it will also actually include the information you have proprietary, so we actually don't have to share with the world. And the question, you can ask is, what is Chih-Tsung's salary? I'm not going to tell you, but it's something you actually can get out of this information because now it's proprietary. And it has evolved further. What's the next evolution? Next evolution is retrieval augmented generation. Why is this so important? Because you can see from this pictorial diagram, it's actually live instantaneous information. It's actually live supplemental data that you can change anytime and add to it, because when you do a search, when you do a prompt question, it will look at the RAG of your local data, Once your locate data actually has it, then it actually sends it to the fine-tuned or the standard classic large language model. So we can see very clearly that this evolution has enabled us to enterprises be able to do things that we want to do without having had to share it with the global world. Now, you see, this is still a question and answer. So it's intelligence, but it actually hasn't gone us as much as we wanted. So the evolution actually we talked about a little earlier was the next step, agents. An agent is basically something that with a chain of thought and actually is able to take one question, do reasoning, and really iterate until you get an answer. So that's an evolution that actually happened within the last 2 years, a year and a half. And finally, this year, we want to share actually, you'll see a very big differentiation. What we call agentic, what we call basically sub-agents and agents. Where the agent itself, you'll see, is actually an orchestrator. And where you have a bunch of sub-agents, which are tools and that takes actions. So we want to share with you the thing is how agents and large language model actually have evolved. And why this is so important. Because what has happened right now, you can see is there's intelligence in agent, that there's orchestration, and then we actually have sub-agents, which actually take the actions. And even though this example is early, you can do parallel, and this actually enables, right, multiple thoughts and deep dive research. So when you do a deep research, you think about you click on it, it actually does a lot of research and then come back with the answer. So this is so important to us. Why? And that's the topic of today's discussion is because as our Cisco's OCP-inspired Cisco 8501, which is based on the 31.2 terabit G200 silicon, that's capable of 64 aggregate OSFP ports, actually is a beneficiary of this generative AI diagnostic future. And if you haven't seen the expo, right, thing is that there's still time you actually should go and see our box that's actually on the show floor. And the next thing is once we know about this whole thing is the key thing about our invention, our solution here is the thing is, as the saying goes, garbage in, garbage out. So the large language model knowledge base is very critical. That's why we want to share with you actually what are the things that you want to train and how you actually want to work on this. So as we start with any large language models, we know there's Llama, there's Gemma, and there's Qwen. So these are actually publicly available large language models. And these are things you can start, which is trained on basically the public space. Next, for us to think about diagnostic is the fine-tuning. We all have software development kits. We all have user guides. We all have register spec. And we all have software abstraction interface. These are really useful information which we can fine-tune. And we saw the previous picture, you can augment your knowledge and be able to do so. And lastly, in terms of very strong knowledge base we talk about here, is the retrieval augmented generation. Their information here actually will change frequently. Will maybe change daily, maybe hourly or monthly. So these are things that we don't fine tune. And these are things that we call the software abstraction interface testing, right? And also the diagnostic test, and also the DVT-XDV test. So these are things we actually use augmentation to create a knowledge base. So this knowledge base is so important to us, as we said, garbage in, garbage out. This is how actually you prevent and having a very important knowledge base. Now, Wei-Jen will actually show you examples of our current limits and future possibilities with this type of knowledge base and how we actually put it into practice.
With the background that Chih-Tsung has covered, we'll move into the operational use of generative AI for diagnostic test development. First, we'll cover the switch test development process and assess on the level of difficulty for generative AI. The traditional steps start with planning and execution on test development. For planning, to test the switch in diagnostic modes, which areas need validation, which components need to be covered, and how should they be operated? What connectivity needs to be checked? How can we cover as many components as possible to minimize test time and provide for the maximum stress conditions? This area is where generative AI performs very well and the difficulty bar is low. There is a wealth of information already out in the public internet, which can be further supplemented through combination of fine-tuning and RAG that Chih-Tsung has mentioned. For execution on test development, this involves traditional steps for creating test cases, mapping physical port topology for board and system, adding traffic generation and checker capabilities, enabling and configuring front panel electrical loopback and optical modules, monitor results, also address when an error happens, what are the steps needed to isolate. The difficulty here is moderate and limited by the availability of driver APIs that are available or not available for PSU, fan, optical modules. Low-level debuggability also requires supplemental information. The subsequent steps are for validation, deployment, and test updates. The difficulty for validation updates of test cases are moderate and similar to test case creation. For deployment itself, it's primarily operational and thus not as applicable. The output from generative AI is shown here for switch test plan generation. The prompt used is, for diagnostic switch testing, which hardware components need to be covered and how should they be operated? The results are shown on the right. Generative AI scores well here, providing test coverage areas and successfully identifies the switch ASIC as the first component, followed by the SerDes PHY lanes as the second component. This description covers port SerDes, the forwarding tables, as well as the buffer memory. The description also highlights to monitor for packet drops and CRC errors. The SerDes PHY lanes are called out separately to run PRBS and collecting eye diagrams. Note that the information here is also sufficient to use as the next level of prompts to generate test cases. Next are the front panel modules, and assume optics are plugged in. Note that it treats the port max as a separate component and requests to check for performance, packet patterns, as well as packet edits. The CPU host subsystem is also covered as the fifth item, and the PCIe interface is specifically called out to run DMA, which we know happens for traffic to and from CPU. Power delivery is also important telemetry that is read out here, including the call out for high load logging of voltage levels on dips. The response rounds off with fans, and including instructions to run at full load for thermal stress and to validate fan speeds with RPM feedback. The operational tips are helpful, prescribing how to fault inject conditions as a test case. Lastly, storage is covered for performance and where leveling information. Information is gathered for logging purposes. Not shown here, but we also queried if there are additional components to test, and generative AI came up with more than 5 more items, including LEDs as an example. Generative AI on its own also provides various tips for critical information logging, such as temperature, power draw, and diagnostic error counters. Notice that they provide tips to fail fast, which can help reduce test time. Now we move to prompts for actual test development. The prompts include write a diagnostic test case for testing power supplies and fans for a Cisco 8501 switch. Write multiple test cases for traffic and also test ACLs, including result verification. Add requests to check for packet rate. That has yielded good results. And internal loopback for isolation has also performed well for the results. Now go into the details. For PSU and fan testing, we asked generative AI to write a diagnostic test case for testing power supplies and fans for a Cisco 8501 switch. It responds well, describing first the test plan. Notice that it calls out first that it relies on pseudocode for potentially abstracted APIs to retrieve the needed information. The background is that their sensors are often exported through SysFS with platform-specific naming, and that there are no standard APIs to leverage like PSI for data plane and ports programming. The code here describes follows the description and gets the fan speed to confirm the switch to the high setting. The voltage supplies have voltage and current readback capabilities, and those are actually read and logged. Here, we provide the prompt to write a C++ test case for setting up for snake traffic using Psi attributes and Psi APIs. This is for data plane testing. This test case configures, on the right, snake traffic leveraging Psi. Given that SAI is a standard through OCP, the information needed for generative AI is readily available to create and configure the switch and monitor to check for the results. This prompt is the same as an additional case and adds ACLs and result verification. Generative AI is just as ready to tackle adding ACLs as well as packet verification, given the rich database of information that's out on the internet for Psi. Conclusion. Generative AI for switch diagnostics is generally good for commonly implemented areas such as switch configuration monitoring via SAI. Speed of implementation is generally faster through generative AI bootstrap. Maintaining code for test development is generally easier and can be faster. The documentation is generated very quickly with low effort, and the quality of results will continue to improve with the help of the community here. Generative AI for switch diagnostics has a gap, which is standard API interfaces for areas such as PSU, fan, optics, and system management as needed. Lastly, the call to action is to grow a set of standard APIs, leverage standard Psi from OCP, and have consistency across platforms. Thank you. We might be out of time for questions, or yeah.
3 minutes.
Okay, 3 minutes, very good.
May I ask, I think earlier your other colleagues shared how to do the fine-tuning, right? Change the model. Could you elaborate that a little bit, like what resource and how do you do that kind of fine-tuning? Is that taking a lot of racks to do that, or it's just a very easy, handy service, GPU service? Thank you.
So fine-tuning we have done actually takes a lot of compute resources. It's a lot more than RAG. So the thing is, you have to bring in the whole model. You actually need a bunch of GPUs. So we don't highly recommend doing fine-tuning a lot, but it's really helpful when you actually are able to fine-tune your functions, your code. So for example, when I did it, it took several days, almost a week, right, to actually fine-tune the model and using it. But it was very effective, much better than actually using RAG. So I do recommend it, but you'll have to have your own GPU compute source.
With like how many GPUs?
My cluster actually has 16.
16?
Yes.
Okay, thank you.
Any other questions?
Yeah, a quick one. So you showed a lot of the stuff for actually generating the test plan. Is there a plan or a methodology intended for how you actually execute these on the switch? Or are you intending on integrating with standard things like MCP? Or will this be sort of on the sort of switch vendor to determine how this actually executes on the system?
So it's a great question. For the Psi side, the Psi testing actually runs just on its own. The ones where you want to test the fans and PSUs, if you look at the code, it actually says, hey, there's a template where you need to provide the APIs for the particular platform. This is where we see that there's a gap. SAI takes care of the data plane very well. For other areas, it's one example is the optics has CMOS, and the registers are there. There's a Yang model. There are ways of accessing, but there are always GPIOs and other system level information that's particular to the system itself. We find that potential gaps there. Yeah.
Cool. Thank you.
Are we good?
Thank you.
Thank you very much.